Loutfi, product lead at Canonical. Many of you would know it as Closer. Yeah. Many of you would know it as the publisher of Ubuntu. But for these first few slides, let's assume I am an application level developer, and I am a simple person. I like simple things. Not too simple, but just reasonable, clean, and efficient. I've heard of confidential computing, and I really like it. So now I have a simple goal in mind. I want to protect my code and data. And I'm emphasizing here my code and data to exclude that I don't care much from a security perspective about the guest OS's code and data, and neither do I care much about the guest firmware code and data. And I know what to do. I'm just going to pick a silicon that I like, an infrastructure provided, and I'm just going to go ahead and deploy my application. And then I also understand that at some point in time, I will need to attest before I can release secrets or accept the computation as being valid. And this is my simple view of what attestation should give me to achieve my goal. About the what should be reflected in the attestation. I wanted to tell me something about the host side, that I am running on a genuine, well-configured CC-enabled machine. And for the guest side, I want to know that my software has been loaded indeed into the TEE as I expect, that it is being and will be updated as I expect, and importantly, that no other software can impact its security state. And then when do I want this attestation? I want it at launch time, boot time, as well as runtime. This very much sounds like something we've seen early in the early days of confidential computing. This sounds like process-based TEEs, something like SGX, where I'm running alone in the TEE boundary. And I looked at this, and I was like, well, it's a great security value proposition, except that I'm going to lose my ecosystem. Do I have suddenly to care about what is the operating system I need to bring with me? What about system resources that I can no more have access to? And then, because I miss my ecosystem, I look into VM-based TEEs, and here they are back again. I only have to worry about running my application the same way I'm using to running it. It's a VM, confidential VM, but at the end of the day, I operate it the same way I operate any other VM. And the ecosystem has benefits. So I decided that I'm going to do the VM-based TEE. Except that I'm realizing that I'm losing some security primitives, guarantees with VM-based TEEs, because now my attestation is, well, it is polluted. Because there are more things that are running alongside me, which means there are more things to attest with my code and data, and it is difficult to reason about that. And also because now I have to think about the lifecycle management of stuff that is not mine. When is the operating system going to be updated? From where am I going to get the reference measurements? What about the guest firmware? This is just way too complex. But I'm determined. I still want to get the best of both worlds, actually. I want the ecosystem of confidential VMs, but I still like the small boundary of process-based TEEs. So this is a point of view that we're hearing repeatedly from customers. And we understand that the world is just a better place when we collaborate. So we are very much for the VM-based TEE approach. But as an operating system, we have been asking ourselves the question, how can we solve or at least help alleviate the security concerns which come with a wide TEE, that is the VM? At a high level, the answer is we need separation of concerns within the confidential VM itself, and we need clear rights and ownership of every piece that runs within it. So for the operating system, the guest OS specifically, what are some guiding principles that we can think about to guide our design for such a perfect OS? Well, to make use of the ecosystem benefits, I definitely need modularity. Not as much as a microkernel, level, but I need modularity. Maybe the kernel needs to be containerized separately from the rootfs, and then I can have my application as a separate container as well. But I also need composability so that I can make it as bloated or as thin as I want it to be. But also security, obviously, is very important. So the containers that I'm going to compose my system out of have to be sandboxed to run in isolation. But we actually see that even if it's quite popular these days to speak about single-purpose CVMs, people still just want to think of CVMs as a normal VM. They're not going to be, they don't expect that they're going to be the only application running within it. So a container, a sandbox, has to also have interfaces to communicate with the rest of the system and other containers in a controlled, secure way, of course. I need to have some meaningful way to provide provenance for the modules that I have. Immutability is very important. Auditability, what I mean is that I want to know if I have a shared resource in the VM, what are all the other modules which are having access to it, and I decide if that's an acceptable risk level for me or not. And very importantly as well, I want transactional updates and rollbacks for every module. So these have been the guiding principles for Ubuntu Core. It's another flavor from the Ubuntu that most people know and use on desktop servers and otherwise. And what you see here is the architecture that we have. Every box is compartment, for lack of a better word. In Ubuntu Core world, we call that a snap. So we have at the very bottom the Ubuntu kernel. The kernel itself is a snap. And it is separate from what we call the gadget snap, which encapsulates the bootloader, the BSP, and some configs. The rootfs for us is a separate snap. We have system snaps in the blue over there. And you can decide how many of those drivers you want to include, and then your application can run as an application snap by itself if you want a single-purpose CVM or along other snaps, other applications. And then composability. Actually, there is no one Ubuntu core. We provide the primitive called model assertion that allows you to compose declaratively what it is that goes into this image. What goes into the system snap? Maybe you don't want, I don't know, some device to be supported. Which kernel do you want to use? And which apps would you allow to run on your image? So already this design is giving us the modularity and composability, but the security primitives also flow from how we define the container. In our case, it's a snap. So snaps are, at the end of the day, SquashFS archives. We bundle them with all of the dependency that the application needs. And at runtime, they implement a security sandbox that is bootstrapped by the same kernel primitives that other container technologies are making use of. For our case, we're using AppArmor as an LSM. We're using SecOps, device cgroups. But in order to allow the snaps to talk to each other and to the kernel snap and the rootfs, we declaratively allow the snap developer to have what we call interfaces. So by default, the snap cannot access anything unless, for example, I'm going to give an example that we can relate to from the desktop world. It wouldn't be able to access your camera unless you declare that it can access the camera. It is immutable because we mount them as read-only, and they are digitally signed and hashed, and we will see how that happens. Snaps are managed by a user space daemon that we ship with Ubuntu Core that's called snapd. And I very much like their transactional updates methodology in which each module or layer is updated independently through deltas. And we can automatically roll them back in case of failure. One way to get hold of snaps today is through a public store that's called the Snap Store. But there is a way to deploy a store only for your organization if that's what you prefer. More security features about Snap Store snaps is, I think I'm going to highlight here mostly the idea of revisions, which is a number that we uniquely identify with each upload to the store. So not only is that every snap has a revision number, but every time you update the snap and you upload it to the store, we give it a new revision number. And this revision number is actually tied to the hash of the snap. This is a very important concept in snaps, which we call assertions. At a high level, these are metadata, signed, verifiable metadata claims about the snap. And they accompany the snap. You can find them on your device if you're curious to see what they look like at Barlib Snap, the assertions. And we have different types and classes of assertions. So you can have statements that speaks about the account that owns the snap, about the build, what were the conditions at build time for this snap, snap revisions for when you upload the new version of the snap, and a bunch of other types of assertions. So this is an example of a snap revision assertion, something that you would get, that will get generated once you have uploaded a new version of your snap. And I'm highlighting here the hash of that particular snap, and you can see other metadata attributes like who owns it, the revision number, and then you see here at the bottom the signature over it. So where does the signature get generated? Simply put, it gets generated in most cases in the Snap Store. On the right side, I'm just showing here a hierarchy of things that live on the Snap Store to support this. And on the left side, we're going to walk through what happens when you want to install a snap and how it gives you integrity. So on the right side, we have an account key that is owned by the Canonical Snap Store. The Snap Store supports having multiple accounts. Every account can publish different snaps. And every snap will have a snap declaration, right? But every time you will publish a new version, you will have a new assertion of type snap revision that will be associated with a hash. So the assertion, it's generated in the Snap Store, and you see here when it is time to download, for example, the Firefox snap, you will not only get Firefox as a snap, but you will also get all the assertions which are associated with Firefox snap. And you can choose to actually download all the assertions locally into your environment and put them in the assertions DB. And when it is time to actually install the snap, this is where things get interesting. Remember the user space daemon, the snapd? Well, snapd will be hashing. Before installation, it will hash the snap, and then it will compare the hash that it will get to a good hash that will be part of the assertions that it has downloaded. And of course, we know that is a good hash because it is signed by a key that we trust. So let's say the snapd decide this is actually a good snap. It will install it, and subsequently it will just create a systemd mount unit, and every time that the system boots again, it will just auto-mount the snap. So I'm highlighting this here too. This is things that are already in place. But because integrity is very important for CVMs, we are considering even more subtle attack vectors. So for example, this verification of hashing and comparing against the assertions, it only happens once. It only happens when you want to install the snap. This is the state of things today. But it might happen that there are threats, there are offline modifications. So my point is that when you boot again, we don't do the same verification again. We just mount the snap as it is. We will only re-verify if there is a new assertion, a new revision, a fresh update that you have uploaded to the snap. But in between those times of refresh and first install, our analysis, well, we concluded that things might still go wrong. We might have offline modifications of the snap or even some runtime ones. So our goal is to have even better runtime integrity for an Ubuntu Core image with snaps. And the primitive we've chosen to implement this is already work in progress, it's almost done, is dmverity. So it works at the block level. I'm not going to go into the details of it, but you just pre-compute a Merkle tree of hashes. You have the root hash and then at runtime, you just compare against the root hash. To be specific, for Ubuntu Core, this is how we are making use of it. This is more interesting. So for on the remotely, we have decided to generate DM Verity data for snaps in the store. So this is either the Canonical store or your store if you are deploying one. And then we put the DM Verity root hash and parameters in the snap revision assertion. So now your assertions will have even stronger claims about the integrity of the system. And we throw away the DM Verity data file. And of course, now that we have these stronger claims, we can do more interesting stuff locally. So we can verify the assertions, regenerate the DM Verity data using the parameters from the assertions so that we have the same expected values. And then we get the pre-computed root hash from the assertion. And finally, if things check, then we mount the snaps with the Verity data as well. So there are interesting things when once we have this, the current work in progress, we're extending the better runtime guarantees to what we call the base snaps, so not yet to the application snaps. And even with that in place, we can do very interesting things. For any VM, confidential or not, we can use this to extend secure boot. So assuming we have a UKI that is signed as part of secure boot, we will have the init ramafs as part of the UKI, and then we are adding there a small kind of shim layer that has access to the trusted key, and that trusted key will be able to extend the verification of secure boot to the root FS. And that's great. Even more relevant for attestation of CVMs, we know that measurements are very important. And what we're able to do with this DM Verity at runtime is powerful. We're able to extend integrity guarantees today all the way up to the root FS. This is a feature that we've actually heard from a number of customers of CVMs, because some of them truly care about integrity strongly, and they want it not just up to initRD, they want it all the way up to the root FS. So with this stronger view of integrity, what we're able to do today, as I mentioned, is integrity protect all the way up to the root FS. And of course, this whole thing is going to be rooted in the silicon root of trust. But as we're working through our journey of better integrity, we're going to extend integrity measures to the application snaps. And we have a right, because snaps are read-only, we have some writable layers which are now encrypted, and it's very interesting for us as well to integrity protect them. And this could be a CVM. This is a CVM that customers want, actually. And it doesn't give them, there are no performance hits. They are not forced to use full disk encryption. They are not forced to use VTPMs with all the complexities that come along with it. And then they can choose to do the attestation once everything has booted, and yeah, they do whatever they want. I personally believe that the security guarantees of this vision for a CVM with Ubuntu Core flows very nicely because of how well the compartment that we define, which is a snap, works with the architecture, the modular composable architecture of Ubuntu Core. But we have seen people deploying confidential stuff with Docker containers, and that's something very much that you can still do with on top of Ubuntu Core. There are actually quite interesting use cases where you can just run a container on Ubuntu Core, or you can put a container in a snap. Whomever is interested, I think these use cases are very well documented on the Core, Ubuntu Core web page. And one other thing that I particularly like about Ubuntu Core is that this is not a new project. It started. It was different when it started, but it did start initially as an OS for IoT devices. And we've been deploying a lot of IoT devices in the field with Ubuntu Core for many years now. And with the confidential computing, I think with ARM, probably going to be the first ones to bring it to large screen devices and to the edge. Ubuntu Core can become a unifying layer to deploy confidential computing workloads on from the edge to the cloud. And because we have years of experience deploying Core for devices in the wild, then obviously enterprises do not just expect that we give them a core image. They want enterprise-grade support for the fleet that is running core. And we have the tooling around it. So we have landscape for enterprise management so that you can have overview of the security state of your fleet. And we have 12 years LTS support for Ubuntu Core as well. So come to think of it, what I've realized is that confidential computing and Ubuntu Core, at some level, at some fundamental level, they are really trying to solve the same problem. And that problem is the acknowledgement that we are living in a digital world in which trust relationships are complex. When I am running, let's say, even a desktop Ubuntu machine, I can no more expect that all the bits and pieces running with me are trusted. Maybe not all of them will be open source. Certainly, I'm not going to have a look at all of them. And the same thing for confidential computing. They have realized that we need to have some separation of concerns. And confidential computing achieves that very beautifully. You can have the infrastructure host side still manage the VM and your workload, but it doesn't have to peek into your workload. So there is this separation of concerns between the infra owners and the VM workload owners. And with Ubuntu Core, we have done the same thing, but on the guest side, if you choose to run Ubuntu Core on the CVMs, because now we understand that the system owners have separate concerns than the application owners. And in that regard, we give them meaningful separation security-wise, while still allowing them to interact with each other when they need to, through the snap interfaces and the other primitives that I've presented. So I invite everybody to give Ubuntu Core a try. We are going to be publishing Ubuntu Core images on some particular public cloud providers, but all the documentation is available for you to start, getting hands-on with it and contributing if that's of interest. Thank you.